Hi guys, welcome to part 3 of the Gearbox tutorial. Today we're going to be working on creating an assembly with the gearbox plate, as well as all the components that fit inside the gearbox. Let's begin by starting a new assembly in Autodesk Inventor. Alright, once in the assembly, let's place 2 of our plates. Alright, before we continue with our assembly, I want to turn off the user work planes, so I'm going to go to View, Object Visibility, and uncheck user work planes. I'm also going to change the visual style to shaded with edges because it makes things a lot easier to see. Alright, now that we're in here, the first thing we want to do is constrain the plates to each other. So go ahead and click Constraint and hover over any 2 circles. So for example, I'd select this one and this one. Be very careful not to select this green point here. This green point here would indicate that we're constraining a point to a point, and that would allow these plates to orbit around each other, when really we want to constrain their inside axis to the other inside axis. Alright, just go ahead and click Apply, X out. Alright, let's drag out one plate. Now you'll notice that we've only constrained this top hole to the top hole here. So if I grab this back plate, I should be able to rotate it around. Alright, let's constrain another set of matching holes. We're going to click Constrain, the bottom bearing hole here, and the bottom bearing hole here. Alright, matches up. Go ahead and click Apply, and X out. Alright. Now what we want to do is import our motors. The motors will be the first part of our gearbox. Go ahead and click Place. Find the VEX profiles that have been downloaded onto your computer. Go to Motors and Electronics and find the sim motor. It is file 217-2000. Now let's rotate it just for visual adjustment. Place 2 of them. Okay, now we can begin constraining the motors. Again, the first thing we want to do is constrain the axes. So I'll select the axis of this motor and constrain it to where the hole is going to be. Same thing on the other one. Apply. Now, in general, I'll be repeating this a lot throughout the video. When you're assembling components in Autodesk Inventor, you want to assemble them in a way that would make sense as how you would assemble it in real life. So after I use my hands to align the motor to the hole, the next thing I want to do is align the bolt holes on the motor to the bolt holes on the plate. Let's go ahead and do that. Bolt hole here, align. Bolt hole here, align. Alright, the final thing I'd be doing in real life is pressing the face of the motor against the face of the plate. So I'm going to hit Constrain, face of the motor to the face of the plate, click Apply. Same thing on the other one. Alright, you can also see that the hole we made for the hub fits perfectly around the hub on the sim motor. The next thing we want to do is import our gears. We're going to begin by taking a look at the gears that we had in our layout sketch. Right click on your plate, hit Open. Let's go to the first 2D sketch in the drop down. And let's take a look at what gears we used. So the first gear is this one. I can figure out what teeth I used by double clicking on the number. As you can see here, I used a 12-tooth gear and the diameter pitch was 20. Back to my assembly. What I need to do now is import 2 12-tooth gears. In order to find out what part number this is, I'll be going to the VexPro website, going down to their gears menu, and finding out the file part number for their gear. In this situation, you can see that the file number is 2172614. Now a little cool fact, the reason that all VEX profiles start with 217 is because the founder of the company was a former student, or I believe former mentor, of Team 217, the Thunder Chickens. That's why all parts on Vex Pro start with 217. Alright, we can see that the file part we need is 217.2614, or we can use 217.3099. The only difference between these two files is that one is aluminum and the other one is steel. So I'm going to go to Place, find the gear in my dropdown, Motion, Gears, Sim Motor Gears is conveniently made a folder, and I'll be selecting 3099 in my case. Let's import two of these. Alright, again, let's do this as if we were making it in real life. The first thing I'd be doing is aligning the gear to the motor. So let's select the axis of the gear and the axis of the motor. Alright, let's do that same thing for the other one. The next thing I'd be doing in real life is pressing this gear up against the inside of the motor, or up to the face of the motor. So let's pull the gears out so we have some space. Click Constraint, and constrain the back face of the gears to the front face of the motor hubs. Okay, that looks great. The next thing we want to do is, I'll be skipping over the rest of the gears, and for now I want to import the bearings. The bearings are really important because it helps us align things up really quickly once they're in. In typical gearboxes, you'll see round bearings on the top hole here, the back hole here, and the bottom hole here. The reason that we use round bearings is so we don't have to use E-clips on our gearboxes. Round bearings, you'll notice, have an inner diameter of 0.5 typically. So let's go to Motion. Am I missing something? Let's just look up bearings. Alright. We'll be selecting for a round flange bearing is file 2172731. So once I import this, you'll understand a lot better of why we use circular bearings versus the hex bearing option that Vex Pro provides. This hex bearing option is right somewhere. We'll be using the round bearing, and you'll see why. Then go to Place, Motion, Bearings, 2172731. Let's rotate these so they're easy to see where they're going to go in our gearbox. So we'll have one here, one bit lower here, and we'll have one in the top right there. Alright, let's begin by assembling these bearings. I'm going to hit Constrain, constrain the round part of the bearing to the round part of the plate, click Apply. Let's do this for all the bearings. The most important part is to ensure that the flanges are on the inside of the gearbox like this. The flanges are on the inside to make sure that the bearings don't fall out of the plate. What holds the plates together are the standoffs. The standoffs hold it together and the bearings hold the shaft in place. Now let's illustrate why we use round bearings. A round bearing has an inner diameter of 0.5 inches. A typical hex shaft is going to be 0.5 inches in width. Alright, now you see if I drag this over here, the hex shaft is definitely not going to fit in the circle. So what we do is, we lathe the ends of the hex shaft so they become round. So if I type in 0.5, you can imagine that we laid these ends off. And now just the end of the hex shaft is round, right? So now this circle is going to fit perfectly inside here. Now, only the end has been rounded. The rest of the hex shaft still remains hex. Therefore, the middle part of the hex shaft cannot slide out, and the ends spin freely. This example is probably better demonstrated in real life and much easier to understand. If you can get someone to do that for you, that'd be fantastic. Next thing we're going to do is constrain the bearings so they fit right inside the plate. Let's go ahead and constrain. Let's select the inside of the flange face and the flange of the gearbox, or sorry, the face of the gearbox, and click apply. Same thing for the bottom one. Alright, now for this back one, or this front one over here, I want to show you guys another type of constraint we can use. All the constraints we've done so far are right here. They're called make constraints. So you can see that in the drawing that it's a face facing the other face. Now, another option I have is this flush constraint. In this situation, the planes are flush with each other. So let's select flush. Right here, the back of the bearing and the front of the plate. You can see that these two faces are made flush. Apply, and let's check the flange to make sure it fits. Perfect. It fits perfectly because the width of a bearing is 0.25 inches and the flange is a 1/16 in thickness. The overall width of the bearing is that quarter plus the 1/16, which is about 0.313. Remember, this number will come handy later. Alright, now that we have our bearings in place, let's import the other parts. You'll notice that I didn't put the bearing in the bottom, in this hole over here. I'll explain later why we leave that open. Okay, the next thing we want to put in is the gear that goes on the top shaft here. Again, we can figure out what gear we need by looking at the drawing we made earlier. So we go to our gearbox plate, and we see that this is our initial gear, and it's connected to this gear right here. Follow it around until we can find a dimension. Right here. And you can see that it's a 42 tooth gear. Let's go to the VexPro website and figure out what file number that is. So we're going to go to Motion, Gears. Let's go to 1/2 inch hex bore gears. And scroll down until we find the 42 tooth gear part number. Right there. 2173216. Back to our assembly. Place. Find our file. 1/2 inch hex bore. 3216. Say OK. And let the file import. Alright. Place 1. Hit escape. Let's begin by constraining the round part. You'll notice that it will be very hard to find a round part of the gear. Even if we try to go in between the teeth, it doesn't select it. So what we do is, we go to the little nub at the end of the gear. Select this, and you'll see that there's an axis that runs right through the middle. Do the same thing for the bearing. Now, their axes are aligned. Click Apply. Alright. Again, just like in real life, we want to put this gear flush against the bearing. So hit Constrain, this back face here, and the front face of where it makes contact on the bearing. Apply. Now, just to ensure that we did this correctly, let's drag this plate out and take a look at how the teeth mesh. You can see that if we adjust the gear teeth here, we can get these teeth to mesh. Fantastic. Let's do the next set of gears. If we go back to our drawing, we can see on the same shaft is not only this 42 tooth gear, but also this gear here, which happens to be 30 teeth. Let's go to VexPro, find the part number, 2172705, and import that. Alright, import one, and let's start constraining it. Remember, your second stage begins on the top shaft and ends on the bottom shaft. When I refer to stages of gears, I'm referring to the combination of driven and driving gears. the first stage refers to how this gear drives this one, and the second stage refers to how this top gear will be driving a lower one. Let's constrain this one. Round to round, hit apply, drag it out, and now we're going to press it up against each other as if we were doing it in real life. Now, just to make it look pretty, we can constrain the inside faces of the hex bore of the gears. We can click one face, make it flush, and make that plane flush with the other plane. As you can see, flush allows them to be in line with each other. If I chose mate, it will give me an error. Alright, let's edit the relationship. We can make it flush and it aligns perfectly. Alright, now you can see that as I spin this gear, that gear should spin with it. Fantastic. The last gear we have to import is the gear on the bottom shaft. Back to our drawing, we can see that we go from our 12 tooth to this gear, and if we follow it around, we can see it connects to this massive gear at the bottom. This giant gear is referring to this dimension. 50 inches divided by 20. 50 tooth gear. Back to our assembly. Vexpro's website. Finding what part number the 50 tooth gear is. It's 2173572. Let's import that. Alright. This constraint should be easy. We do the axis of this to the axis of the bottom bearing. The hard part is aligning this bottom gear perfectly with this one. Just like I used earlier, we can use a flush constraint. I use constraint, make this face of the gear flush with the face of the other gear. Now you can see that these two gears are perfectly in line with each other. Alright. Finally, we can add the last component of our gearbox, the sprocket. Sorry, the last moving component of our gearbox, the sprocket. The sprocket is going to be transmitting power to all other parts of the drivetrain. This is really important because it's going to make sure all wheels on the drivetrain get roughly an equal amount of power versus the drivetrain just being powered by one set of wheels. In our situation, we'll be using a number 25 tooth sprocket. Some teams choose to opt in for belts, and some teams also like to go for number 35 sprockets. I'll be using a number 25 sprocket as to essentially make it a lot easier to tension. Some teams find that debatable, but in our experience we found that 25 is a bit more easier to work with. Alright. We need to find a 1/2 inch hex bore sprocket with the smallest number of teeth. It happens to be this one right here. 2172642. Let's import one of these. Motion, sprockets and chain, number 25, 2172642, I believe. Alright, let's import one of these. Now, all we have to do is constrain this sprocket to that gear. Axis to axis. Let's drag that out. And let's constrain this back face to this gear. My bad. You'll notice that I've made a mistake here. If you ever need to correct a mistake you've made in your assembly, go to your selections right here. I can go to selection 2, edit what I've chosen. Instead, I'll be choosing... so the problem that's occurred here is that it's assumed that that's the constraint I wanted originally, which it's not. So the sprocket is blocking my view. I'm going to cancel. It pops back out. Let's try this again. Alright. Next thing I might want to do is make it look nice, and we can make these flush. If it gives you an error like this, cancel the operation, manually align it until it's pretty close, and try again. It should allow you to do it. If it doesn't allow you to do it, just leave it alone. It's not completely unnecessary. Alright, now we have all the main features of our gearbox. What we can do now is start to bring in this plate. Instead of making this plate completely flush up against the sprocket, we're going to have to do something a little different. What goes around sprocket is chain, as you might see from bikes or other types of vehicles. So what we need to do is leave a small gap for the chain to go around the sprocket. Typically, we're going to use a 1/4 inch gap. So we'll constrain this plate to the face of the sprocket, and in your offset over here, let's type in 0.25. Fantastic. Now you can see that there's a very visible gap between the sprocket and the plate. Now, let's insert the other components. The first thing we want to insert is our standoffs. Don't worry, the hex shafts we'll get to later, but for now let's insert the standoffs. We create the standoffs by looking at the distance between the inside of the two plates. So let's go to Inspect, Distance, the face of this plate, and the face of the other plate. As you can see, it's 1.67, a relatively skinny gearbox. Let's go to My Home, create a part, start a 2D sketch, and begin making our standoff. Now, typically on our team, we'll be using Thunderhex to make our standoff. You can check this drawing on Vexpro website, but I have it memorized so you can follow what's in the video. 0.5, and the corners are rounded to a radius of, or diameter of 0.5414. Let's delete the dimensions and trim off the excess. Now, on top of this, Thunderhex shafts also have a 1/4 inch hole in the middle. This allows for easy mounting for standoffs. Let's go to Circle and add a 1/4 inch hole right in the middle. Alright, now let's extrude it to the length we had before, which was 1.67. Alright, add a little color. And save this as our standoff. So I'm going to call it Gearbox Standoff version 1. Fantastic. Now we can import this in our assembly and start constraining it. If you don't see any files and you're sure you've saved something, make sure your files of type are all files. We're going to be using 4 of these. Alright, before I continue, I'm going to save this just to make safe. Fantastic. Let's continue constraining our standoffs. Again, we're going to start by doing concentric constraints. We're going to constrain this axis to this axis, apply. This axis to this axis, apply. And finally, the bottom two. Be very careful that you select the right holes. I'm not selecting this hole here, but this one on the outer edge. It is extremely important you select the right holes, just to make sure that you represent what's actually going on in real life. Alright. Fantastic. Now, you can see why we use CAD in many applications. Our CAD is illustrating that this standoff is about to hit this gear. There's a few adjustments we can make to make sure this doesn't happen when we go about building this in real life. A similar problem is occurring at this point here. Let's go about fixing this. So what we're going to do is, we're going to open up this gearbox, right click, open, my bad, and let's edit the base sketch. Originally we had settled for a diameter of 0.6. If we increase this to 0.65, we might be able to fix our issue. Oh, that is not good. Alright. Alright. Since Autodesk Inventor is being so finicky right now, I can adjust the bottom ones. That's good. So the bottom ones will be fixed. The top ones, on the other hand, we'll do a different kind of adjustment. Possibly I can change this to 0.65. Great. Everything looks good to me. Let's finish the sketch and see if the plate updates accordingly. If there's errors, accept them for now. Let's fix the extrusion here. Let's take a look at the errors that occurred. Go back into the sketch and fix those errors. As you can see here, we have some interfering lines. We can go ahead and trim these off. Alright, let's finish the sketch and go about making your gearbox plate. Go back to your extrusion profiles. As you can see that it's not allowing us to select this portion again because of the open circle that we have there. Let's go back to our sketch and fill in this gap with an arc. Arc center point, close it off from here to here. Alright, this should fix our issue. Alright, now you can see, right after closing the gap, everything automatically updated. The only small issue we have is the fillet missing in this corner. We can easily fix this by adding the fillet manually. Awesome. Let's save this and continue with our assembly. You'll notice that our assembly has shifted slightly. If you shake any of the parts, it'll automatically update. You can see how the gearbox standoffs adjusted right there in the corner. Everything is more spaced out, and now the gearbox standoffs don't interfere with our gear. Let's continue by constraining the face of the standoffs. This face will connect to this face. This face will connect to this one. And same thing for the bottom two. Alright, just to make this a bit more aesthetically appealing, let's make these two planes flush. Alright, and the bottom two as well. I don't like how it rotated my perspective, so I'm going to cancel that and make a quick adjustment. I'm also going to undo the flush constraint I did back there. I'm going to ground one of the plates, right click, ground it, and now you'll see that I cannot move any component of the gearbox, only rotate them in place. This will ensure the perspective of any of my parts won't change. Alright, now we have many of the major components of our gearbox. Let's add the last few. One thing we need in the front is a West Coast bearing block. This bearing block will allow for easy mounting to our drivetrain frame. If we go to the Vexpro website, it will be under VersaFrame and West Coast bearing blocks. You can read all the information provided here to help better understand how these bearing blocks work. In our case though, we will be using this one in our gearbox. 2173634. Go ahead to place, find the file in Vexpro's files. VersaFrame, West Coast bearing block, 3634. Place this here. Now one thing I want to show you guys, earlier we changed our visual style from realistic to shaded with edges. If I change it back to realistic, take a look at how hard it is to see the edges on the West Coast bearing block. Extremely hard, right? That's why we use shaded with edges. Let's go back to assemble and constrain this. We're going to constrain it concentrically here and here. Drag it out a bit. this little nub right here is the same outer diameter as a bearing, which would fit in right here, 1.125. So what we can do is do it in two ways. This will be my preferred method, is connecting this outer face to this face right here. And now, finally, this bolt hole that we made here aligns perfectly with the bolt hole here. Fantastic. Now our West Coast bearing block is right in place. The last thing we need to create is the shafts that go in our gearbox. These shafts are what is going to turn the gears in our gearbox. We begin by making the shafts by taking a look at what distance they'll be covering. They'll be covering the outside of one plate to the outside of the other plate, which will be 2.17. Let's go to My Home, Start a Part. Instead of starting a new part completely, there's another method we can use. Earlier, we created a standoff that fits the exact profile of the shafts we're using. So we can do File, a Save As, and let's name this as Gearbox Top Shaft, version 1. Save this, and go about editing it. So the length of this is 2.17, from one end of the gearbox to the other. Like I mentioned earlier, that hex will not be able to fit inside that round bearing. So what we need to do is essentially lathe the end off in CAD. So let's start a 2D sketch on one end. We want to lathe it down to a diameter of 0.5 inches. So we make a circle like that. And then we need to make a circle that's bigger than the whole thing itself. And you'll see why in just a second. Finish sketch. We can extrude, click on this, and retract it. You can see that we've now created a round shaft. But how much do we need to extrude this by? I mentioned this earlier as well. The width of a bearing is 0.313 inches. That accounts for the 1/4 inch thickness of the plate and the 16th thickness of the flange here, for a total thickness of 0.313. So let's extrude it to that length. Alright, now let's repeat the process for the other side. Extrude it. Cut extrude. Okay. Again, just to make it a bit more realistic, let's change the ends to as what they would look like if we did this in real life. Alright, let's save this. Now let's import this into our gearbox. We're going to assemble, place our top shaft, and constrain it to all the little components that we have within the top set of items. So let's do a constraint that's concentric with here and here. And again, we can use the flush constraint here and here. You can see clearly now that the shaft goes through both sides and is flush to both ends. Again, for aesthetic purposes, we can rotate this and constrain it so it fits perfectly inside our gears. Hopefully this will allow me to do that. Alright, I guess not. That's fine for now. Let's add the bottom shaft. The bottom shaft we cannot decide yet because it needs to go to the output wheel. So for now, we'll not put anything in the bottom. When I refer to the output wheel, I'm referring to the wheel that's going to be driving our drivetrain. The last thing we need in our gearbox are the spacers. These spacers are going to go in here to ensure that these gears don't slide around. So let's go ahead and inspect the distance between the gear and the plate. Sorry, the gear and the bearing, and create spacers out of this. So 0.549. Let's make a part, start a 2D sketch, and make these. Now, these spacers are going to be 3D printed, so we can customize these to however we'd like. We're going to start by making the hex 0.55 and the outer circle 0.65. Sorry, 0.75. Finish the sketch, and let's extrude this so it fits perfectly inside. Forgot the number, so let's inspect the distance. 0.549. Extrude 0.549. Add some aesthetic quality to this. And save it. I'm going to save this as the top shaft spacer. Alright, let's import this and constrain it. Alright, let's do a concentric constraint with this and the bearing, or the shaft. And then let's do a face-to-face constraint to the flange here. Let's move this out of the way first. Constrain this face to this face. Alright, let's repeat this process for the bottom. Even though there's not a shaft in here, we know that the distance between these two things is going to remain the same. The only difference here is that the spacer that we import here is going to have to extend quite a bit because it goes through the whole west coast bearing block. Before we move on with this, let's put in the bearing that fits inside the bearing block. You can either go on VexPro's website or memorize the file number, but it is a half-inch hex bearing, which happens to be file 217-3875. Let's import this. Let's do a concentric constraint to the west coast bearing block. Drag it out and do a flange constraint right here. Zoom in, ensure that you selected the right face, and constrain it to the inside face of this west coast bearing block. You can see that the west coast bearing block was designed perfectly to house this. This was to ensure that the shaft that runs through here is supported equally on all of its points. Let's constrain this to the bearing, to the gears, and see if it lines up. It doesn't, which is perfectly fine. Alright, now let's create our first set of spacers on the bottom shaft. We're going to inspect the distance between the face of this sprocket all the way to the inside of this bearing. Now you see that I have an issue finding out where the inside of this bearing is. We can go to View, Half Section View, move this inwards, drag it in slowly until I can see the inside. Click Check. Let's go back to Inspect, Distance, the face of the sprocket, and the inside face of the bearing. 1.303. Let's go back to View and End Section View. Now we need to create a spacer that long. So let's go to My Home. Instead of going to My Home, let's do a Save As of the other spacer we made. File, Save As, and we can do bottom shafts. We can call this bottom shaft spacer. Alright. Now, forgot the length, so let's do this one more time. Half section view, drag it in until you can see the bearing. Check, inspect, distance from the face of the sprocket all the way to the face of the bearing. 1.303. Let's change the extrusion of this to 1.303. Click OK. When I go back to my assembly, I may not want to end my section view just yet, just so it's very easy to constrain. So I'm going to hit Assemble, place, find my spacer file, and let's constrain this. You can see that in the side picture there, it's quite short. I did not save this, so let's go ahead and save that, place it again, and it should update. Now you see that it's become longer. Place it, and let's begin constraining. Let's do a round constraint to here, to anything on the bottom. Drag this out, and we know that it must touch either the bearing or the sprocket. Either one suits you. Whatever's easiest to constrain, go for that. You can see that it fits perfectly between the sprocket and the bearing here. Click apply. Let's go to our view and end the section view. Alright. The last thing we need to do is add a spacer to the back. So we're going to do an inspect. Distance between here and here. 0.498. Let's go to our spacer, do a file, save as, bottom shaft spacer V2. Let it load. Change the extrusion number to 0.498. OK that. Save it and put it into our assembly. Let's constrain it. Concentric constraint here into the bearing. And let's do a face constraint from here to the gear here. Again, you can see it fits perfectly between the bearing here and the gear here. Alright, it seems that we have every component of our gearbox. The few things we are missing are the bottom output shaft, which we'll import once we assemble it to our drivetrain, and all the bolts that mount everything together. If you would like, something that we would do in the actual build season is import all of the bolts as to ensure that nothing interferes. For example, we would put in the bolt that connects this hole to the motor, and the bolts that connect the standoffs to the plate. Besides that, we've finished part 3 of the Gearbox tutorial. Look forward to another video illustrating how we will attach this to the drivetrain and how the plates can be CNC'd. Thank you.